In this lecture, I'll be talking about control, optimal control, and the cost to go function, and specifically KL control. So this is where there is, our control is stochastically affecting which outcomes we take, which actions we take. So we'll be concerned with the case where we have some set of actions, U, which is, typically this could be which drug to use, drug used, or coin tossed, or which engine is actually activated, right? So in a control sense, right, this is the actual kind of engine applied to the plane, right? This is the actual outcome of our attempt to control the system. And there is some prior on these actions, which is the prior probability of a particular action being used. So we might consider one drug to be inherently better than another, and so we have some kind of prior bias to a particular drug. Or it might be that they're all kind of the same, and so this is initially uniform. So that's kind of usually the case that we'll have. And then the idea is that we can affect some control, which I'll denote eta, and this is this changes the probability of an action. Right, so the probability of an action is given by this control, and then there's some cost on the control, and the cost in this KL divergence framework. So the KL cost, right? We have that dKL is given by the KL divergence between PU and the prior, and if you do this out, this is equal to the expectation of this control exponent. And this is actually, there's some temperature factor here, which tells us how to convert this entropy into the cost. So yeah, this is multiplied by some temperature. Okay, so the picture we have of our state evolution is that we have a particular state at xt, and there are these other states, which we might call A, B, C, D, right? And right, so if we choose one action, there's some probability of us going from x of t, so then maybe PA1 is the probability of going to state A given x of t, etc. Right, so given control 1, we have this propagator that just goes like this. Oops. Right, and we might imagine also a different control, a different action might lead to a different propagator with a different set of possible outcome states. Right, so U2. Right, and so there's some, and these states are weighted differently. It's just given some action, x t plus 1 is equal to c or whatever. Right, so this action determines the probability that the next state will be one of these possible states. Right, so okay, so let's calculate the cost. So in general, we have some terminal states, which I'll denote by these open circles. Right, so these are terminal states x in the terminal state class. And for these states, we know the cost already. So j of x in the terminal state class is kind of already given to us, is known. So this is just saying at the endpoint of our dynamics, we know kind of where we stand. We know how much cost we have left to take on. Often this is just zero, and that all the cost is accumulated over the course of the dynamics, right? So then we have these states, which can evolve into these terminal states, right? And then we have other states that can evolve into these states, right? And so what happens is J, our information about the terminal condition, is kind of moved backward in time until we know, essentially, the cost to go on the state we're interested in. So in general, the cost is a function of these different paths that we take, these different transitions. So, we could have transitioned this red path first, and then maybe we use a different control here, or take a different action, and we have this blue action here. And it's helpful in this discrete case to use this picture that's similar to kind of the minimum path procedure, where you're trying to find the minimum path between point A and point B. it's the same kind of dynamical principle where the costs are on these transitions, right? So these edges have a cost. That's a function of the start state and the end state. And also which action we took when we got from one state to another. So, overall, so these are kind of the propagators, right? This is k of u2. Right. So, which action we take defines a particular propagator, and yeah. So we have these propagators on our states that are also dependent on our actions. Right, and this could be what observations are made, what drugs are taken, etc. So in general now, if we know the cost on states x of t plus 1, we're just trying to figure out, so we know j of x of t plus 1, and we'd like to figure out what j of x of t is. Right, so figure out one step in this recursion backward in time from the terminal conditions. So the cost at given a particular control, the cost at x of t given a control is equal to the probability of an action given that control times the expected control when at the end of the transition. I mean the expected cost to go at the end of the transition. So this is so the cost to go when you reached your final state plus the cost you've accumulated as you've crossed from your initial state to your final state. So, what do I want to say next? Oh yeah, so, right, and now the cost to go at x of t is equal to the minimum over your possible controls, let's see, of x of t. And it's subject to the constraint that, of course, the sum of pu is equal to 1, right? So we'll enforce this constraint with the Lagrange multiplier. And just optimize. So first thing I want to do is define this whole thing, this expectation here, as the energy, right? So that will play the role of the energy. You see, the control doesn't actually appear here; only the action appears here. So the control is all inside the probabilities. So so the energy of a particular action is just the expected cost to go if a particular action is chosen. It's given by the by the sum over the sum over x of t plus 1 of k of u. So the propagator associated with a particular action times right. So once you define this thing, then the cost. Sorry, this is big C. This is equal to the sum of pu of I forgot the KL piece. So there's also this 8s of u plus this thing. All right, so this is equal to the KL piece. So that's the KL cost times the temperature plus the energy, right, which is just that kind of big thing that we just defined. And now we minimize this thing subject to the Lagrange multiplier constraint. So j of x of t goes min over eta of the sum of u by u eta u times t plus epsilon u. And then we also have the Lagrange multiplier constraint. Okay, so this is mu. This thing is minus 1 times lambda. Right, so this is your Lagrange multiplier constraint that your probabilities be normalized. So this is a standard max entropy kind of calculation, and the result is kind of always the same, that you have that P of u is equal to pi. This is kind of the density of states, E negative epsilon u over t divided by the partition function. Or equivalently, P of u is equal to pi of u e to the negative free energy minus the energy over temperature, where the free energy is equal to negative T log Z. Okay, so that's kind of what's going to happen here. But what's interesting is when you plug the solution back in, 8 of T, well, the Lagrange multiplier, of course, this part all goes to 0. And so you're left with J of x of T is equal to the sum of u e to the phi minus u over t. Sorry, I'll just write this as it's not going to matter in the end. It's going to be pu, right? It's a function of the optimal control. And then we have this A of u t plus epsilon u. All right, and kind of the cool thing is plus lambda times 0, right? The Lagrange multiplier condition is satisfied at the optimum, and this becomes phi minus epsilon u over t times t plus epsilon u, which of course the epsilons just cancel, so this becomes sum of u pu phi, which of course is just equal to phi. So the free energy actually ends up being the cost to go, which is kind of this amazing feature of the KL control problem that is preserved in both our case and in Todorov's case. So let's talk a little bit more about these transitions and where the cost is going, right? So I find it easier to think about these transitions as the cost being on these edges between states. So this is x of t, this is c of x of t, and x of t plus 1, right? Which edge is it, and which action was taken to get from state 1 to state 2. But it's equivalent to thinking about, okay, if we have a cost, we can imagine it being applied at the tail of this thing, right? And if that's the case, this, so in this case where we only care about the cost as we leave a state, this becomes only a function of the initial state, right? Which means that when you have this propagator average, oops. When you have this propagator average, this of course just becomes equal to just c of x of t. But you could just as easily think about, you have a state, and you could just as easily think about the cost as being applied when you enter the state rather than when you leave the state. And in that case, c of x of t, well, we get a slightly different cost function. So the j, j is slightly different in this perspective, just because we're keeping track of the cost at a slightly different time. So j of x of t here is equal to So j of x before x of t is equal to the sum of x of t plus 1 of j x of t plus 1 plus c of x of t. But you could also think about applying the cost at the head, and then you have a slightly different recursion relation. That basically the cost to go and the applied cost are both in the inside the expectation. And these two j's, one is calculating the cost before the state cost is applied, and one is calculating the cost after the state cost is applied. So you can check for yourself that j x of t and this other j of x of t differ just by the state cost. Whoops, the sign goes this way. No, j of x of t is bigger than this one. So yeah, this is a minus here equals to c of x of t. Right. So the recursion relation is really the same. It's just a matter of where exactly you want to keep track of when the cost is accumulating. Is it accumulated before you while you're entering the state or while you're leaving the state? But unambiguously, you can always think about the cost as being on the edge itself. And in the case where we have multiple channels that can lead to the same final state but could potentially have different costs, in the case where we have multiple drugs, it's important to think about the cost as being on the transition or being on the action. And of course, you could always augment your state space to include the transition itself, but that's kind of not really necessary to the formalism. Anyway, so that's all I wanted to say about that problem and that discussion we had earlier. So just to recap, these x's are, in the learning case, of course, these knowledge states, right? They actually include information about the state of the system and the dynamical parameters. And they depend in general on all observations we've seen up until that point. And now we've seen how we can define a KL, right? So we have a KL cost formalism that's different from Todorov's. It's more general in the sense that these U's, where we can control, they're controlling which propagator to use. And so we don't actually have to control every possible outcome, right? So it's a lot less specific than the Todorov control. And that means it's applicable to the case where, in the learning case, we can't control what observations we see and how we perform our Bayesian updates. So in the end, we want to be able to define what space we can actually control and distinguish it from the dynamics. So, but the result is up till now is basically the same, that j of x of t is equal to this free energy object. And in the Todorov case, right, you can exponentiate both sides here, and you get divide by t and exponentiate. And in the Todorov case, this becomes a nice linear problem, but here we don't have that structure. Right? We're left with the sums of exponentials, where the propagator actually lives up here inside the. Whoops! This is not eta. This is energy. So this energy is, of course, this average over future states given a particular choice of propagator.